Okay, so in this video, we're going to look at the next convergence test. This is known as the integral test. You can find this in section 9.4 in our textbook. And so to begin, let's consider this example that says, show that the sum of 1 over n, as n goes from 1 to infinity, diverges using an integral. Now we recognize this as the harmonic series. And in section 9.3, we argued why the harmonic series diverges using an inequality. Now here we're going to argue why the harmonic series diverges using an integral. And so to begin, let's consider the curve y equals 1 over x on the interval from 1 to infinity. And note that 1 over x is the continuous version of the sequence that we're summing here, which is 1 over n. All right, and what I'm going to do now is form these blue blocks. Okay, so note that the width of each block is 1. And the heights of the blocks are the heights on the red curve at the left endpoints of each one of these intervals. So the first block, that has a height of 1, because that's the height on the red curve when x is equal to 1. The second block has a height of a half, because that's the height on the red curve when x is 2. And then the third block has a height of a third, and then we have a fourth, a fifth, so on and so forth. Okay. Also note that since the width of each block is 1, the area of each block is equal to its height. Okay, so the area of the first block is 1, the area of the second block is a half, the area of the third block is a third, then a fourth, a fifth, and so on. Okay, so the areas of these blue blocks, in fact, are the terms of the harmonic series. All right, so now let's compare those blue blocks to the area bounded by this red curve in the x-axis over the interval from 1 to infinity. Then that's what I've shaded here in yellow. And looking at this picture, okay, we have the following inequality. If I sum up the areas of the blue blocks, well, those are greater than or equal to the area under the curve, y equals 1 over x, on the interval from 1 to infinity. Okay, now if I expand this, on the left side, as we just noted, right, the sum of these areas is really just the harmonic series. Now on the right side, okay, I'm looking at this improper integral where I'm integrating 1 over x from 1 to infinity. So I can go ahead and compute that integral. And the integral of 1 over x, well, that's just the natural log of the absolute value of x. And here we're going to evaluate at 1 and at infinity. Okay, now on the left side, I've just replaced the harmonic series from its expanded form to this expression in sigma notation. Okay, so now on the right-hand side, what's going on here? Well, when I evaluate at infinity, what I'm really doing there is I'm taking the limit of the natural log as x approaches infinity, right? And the natural log, well, it blows up, right? It approaches infinity. So what we see here is that this expression on the right actually diverges to infinity. Okay, or put another way, this improper integral is divergent. Okay, and since the harmonic series is bounded below by something diverging to infinity, that implies that the harmonic series itself then diverges to infinity, and that completes the argument. All right, great. So now let's go ahead and look at another example. It's pretty similar, but there's a few key differences. So for this example, we are asked to show that the sum of 1 over n squared converges using an integral. Okay, so notice now there's a square on the n, and this is a convergence series as opposed to what we saw with the harmonic series, right? That diverges. Okay, so the square on the n, well, that's going to make these denominators larger, right? So making the corresponding terms smaller ultimately than what we would see with the harmonic series. And so the loose intuition here is that, well, the square is going to amount to these terms, the 1 over n squared terms, to approach 0 at a fast enough rate so that the sequence of partial sums for this series will settle down and give us a finite sum. Okay, that's the, again, rough intuition. To make that more precise, let's use a similar integral argument like we saw in the first example. So consider this curve y equals 1 over x squared over the interval from 1 to infinity. And now I'm going to look at these green blocks. Okay, so again, width 1. But now the heights are going to be the heights on the blue curve at the right endpoints of each one of these intervals. And I'll say why I'm using right endpoints as opposed to left endpoints here in a moment. Okay, so note here that for the first block, okay, its height is the height on the blue curve when x is 2. So that's going to be 1 over 2 squared. For the second block, that's going to be the height on the blue curve when x is 3. So that's 1 over 3 squared. And then 1 over 4 squared, 1 over 5 squared, and so on. And again, since the width of each block is 1, the area of each one of these blocks is just simply it's equal to its height. Okay, so the areas of these green blocks are giving us all of the terms of this given series except for one, right? And that term that we're missing is just the first term, which is equal to 1. And I'll address that issue here in a few moments. Okay, but for now, let's go ahead and compare these green blocks to the area under the blue curve and above the x-axis on the interval from 1 to infinity. That's what I've shaded here in red. And now we have the following inequality, right? The sum of the areas of the green blocks is less than or equal to the area under the curve y equals 1 over x squared on this interval 1 to infinity. Okay, so let's expand this out. And here we're seeing that I get this sum 1 over 2 squared plus 1 over 3 squared, so on and so forth. Okay, on the left. On the right, I have this improper integral where I'm integrating 1 over x squared on the interval from 1 to infinity. Okay, so again, I'm missing the first term of this series on the left side. Okay, so what I'm going to do for the next step is just add it in. So add 1 to both sides of the inequality. And see, now what I have on the left side is this given series. And so on the left, I have the sum of 1 over n squared as n goes from 1 to infinity. On the right, I'll go ahead and compute this integral, right? The integral of 1 over x squared is negative 1 over x. And now when I go to evaluate at infinity, again, I'm taking the limit of negative 1 over x as x approaches infinity, and that's going to go to 0. Okay, so we go ahead and evaluate. And I'll get a 0 there. When I plug 1 in, I'll get a negative 1, but it's being subtracted. So that implies that this improper integral here converges and has a value of 1. So altogether there, that says that this series is bounded above by 2. All right, so what's the big takeaway from that? Well, two things to point out. One, this sequence of partial sums for this series, so our sequence S sub n, okay, it's a monotonically increasing sequence. And so this bound right here implies that this sequence of partial sums in particular is bounded above by 2. And I claim that those two facts together imply that this series converges. Okay, so here's a visual to help us spell that out in a little more detail. So here I'm plotting the sequence of partial sums S sub n. Okay, S sub n is just the sum of 1 over k squared as k goes from 1 to n. So S sub 1 is just 1. S sub 2 is 1.25, right? That'd be 1 plus 1 over 2 squared. S3, 1.36, and then a bunch of 1s. So that's 1 plus 1 over 2 squared plus 1 over 3 squared. Okay, and so on and so forth. Note, as I increase n, okay, these partial sums are going to increase. And that makes sense, right? Because as I increase n, well, I'm just adding on more positive terms. So the sequence S sub n is monotonically increasing. And again, this bound that we just showed, right, through this inequality argument, says then that the sequence of partial sums is in fact bounded above. It's bounded by this number 2. So those two facts together imply that this sequence in blue is going to have to level out somewhere. It cannot continue to grow without bound, right? It's going to have to level out. Now, this does not necessarily mean it's going to level out at 2. In fact, it doesn't level out at 2. It happens to level out at pi squared over 6, and that's not in any way an obvious fact. So here, just to illustrate, if I plug in a really large number, let's say 10,000 for n. Okay, so pi squared over 6 is 1.64493 blah blah blah. Okay, the 10,000th partial sum is 1.644 0.4483, blah, blah, blah. Okay, so you can see that at least it's plausible that this is in fact the limit of this sequence of partial sums. Again, it's not obvious and it's not a particularly easy fact to prove. I will come back to this result though a little bit later and say a few more things about it. But in any event, the big takeaway for us, right, is that the sequence of partial sums in blue here converges, and so by definition that means that this series converges, and that's really what we were seeking to prove here. All right, great. So now what we're going to do is just generalize these two arguments, and that will lead us to what's called the integral test. Okay, and so here's the statement of the integral test. So it says, let f be a continuous function such that f of n is equal to a sub n for n greater than or equal to 1, and that f of x is greater than or equal to 0 for all x on the interval from 1 to infinity. So in other words, f is non-negative, and f is decreasing on the interval from 1 to infinity. Okay, so if these two conditions are satisfied, then the following holds, right? If this improper integral from 1 to infinity of f of x converges, then so does the associated series of a sub n. And if the improper integral from 1 to infinity of f of x diverges, then so does the associated series for a sub n. Okay, so to illustrate there with these two examples, in example 1, well, we saw that this improper integral diverges, and then through that argument using inequalities, we were able to show that the associated series here of 1 over n diverges. Okay, now in the second example, the improper integral there converged. Okay, so then again, we were able to use some inequalities to argue why the associated series converges. Okay, now in the next two videos, we'll just look at a few more examples of how this result can be applied. But the nice thing here is that if we can determine the convergence or divergence of this improper integral, and this function f does satisfy these two conditions, that will allow us to determine the convergence or divergence of the associated series. All right, well, that's a good place to stop. I will see you in the next video.